Hello everyone, my name is Lin Tao Peng. I am very glad to share our work, Uncertainty-Driven Spectral Compressive Imaging with Spatial Frequency Transformer with you. We will present our work in the following order: problem statement, motivation, method, results, and ablation study. Our work is based on the snapshot compressive imaging, or SCI for short, theory. The typical SCI system consists of two parts: hardware encoding and software decoding. As shown in the figure, in the encoding process of an SCI system, the 3D data cube of the target scene is modulated by different masks and then integrated into a 2D compressed measurement. In the decoding process, the coded measurement captured by the SCI system is sent to the algorithm, either optimization-based or deep learning-based, along with the masks to recover the 3D data cube. For hyperspectral SCI, the most commonly used imaging system is the Coded Aperture Snapshot Spectral Imaging System, or CASI for short. The figure shows the imaging process of a single dispersion CASI system. The 3D data cube of multiple spectral bands from the target scene is first modulated by a fixed mask and then shifted by a disperser. Next, the spectral data are accumulated pixel by pixel on an image acquisition device to obtain the final compressed 2D measurement. Recently, learning-based hyperspectral image reconstruction methods have demonstrated promising performance. However, existing learning-based methods still face the following challenges. First, they rarely consider both the spatial sparsity and interspectral similarity priors of HSI. Second, they treat all image regions equally, ignoring that texture-rich and edge regions are more difficult to reconstruct than smooth regions. Third, although the transformer has achieved satisfactory performance in HSI reconstruction tasks, the computational complexity is quadratic to the spatial size. This burden is non-trivial and sometimes unaffordable. Naturally, the following question arises: how to embed both the spatial sparsity and interspectral similarity prior into the learning process while maintaining the linear complexity? How to achieve content-based adaptive HSI reconstruction? To address these issues, we propose an uncertainty-driven HSI reconstruction method termed Specformer, specifically inspired by the spatial sparsity and interspectral similarity nature of HSIs. We first introduce frequency-wise self-attention, FWSA, a conceptually simple but computationally efficient architecture which can calculate self-attention along the spectral dimension with linear complexity, modeling the interspectral long-distance dependencies and capturing the interspectral similarity of HSI. Next, we use a parallel design to combine it with the spatial-wise local window self-attention LWSA module to form a basic block termed spatial frequency block, or SF block for short. LWSA module can model the spatial sparsity and guide the network to focus on the spatial regions with dense spectral information. Parallel design helps the SF block to model cross-window connections and expand its receptive field while maintaining linear complexity. We insert the SF block as the main building block in a U-shape architecture to form our Specformer. In addition, considering that texture-rich and edge regions in HSIs are more difficult to reconstruct, we introduce an uncertainty-driven self-adaptive loss function to reinforce the network's attention on those regions. As shown in the figure, we divide the training of the network into two stages. In the first stage, the network estimates both the HSI cube and the uncertainty map. In the second stage, the uncertainty values are used to generate a spatially adaptive loss to guide the network to prioritize the pixels in the regions with rich textures and edges. To evaluate the performance of our Specformer model, we conducted extensive quantitative and qualitative experiments on the CAST and CAVE datasets. We compared the results against 11 existing spectral reconstruction methods. As demonstrated in the table on the left and the figure on the right, our Specformer achieves state-of-the-art performance in HSI reconstruction while also reducing computational and memory costs. This figure shows the visualized HSI reconstruction results of 7 SOTA methods and our technique. We can see that our Specformer can accurately reconstruct the details of texture-rich regions and edge regions, as well as preserve the spatial smoothness of the homogeneous regions. In addition, we plot the spectral density curves corresponding to the picked region of the green box in the RGB image. The highest correlation and coincidence between our curve and the ground truth demonstrate the spectral-wise consistency restoration effectiveness of our Specformer. We further applied the approaches to real HSI reconstruction. The reconstruction results on real measurements are presented in this figure, from which we can see that compared with existing methods, our Specformer technique produced higher reconstruction quality in texture-rich and edge regions. Meanwhile, SpecFormer also produced better performance in suppressing noise. To validate the effectiveness of each component in the SpecFormer network, we conducted a series of ablation studies. We can see that the absence of any component in the SF block will result in performance degradation, which demonstrates the effectiveness of each component in the SF block and the effectiveness of their combination. In the picture on the right, step 1 represents the HSI reconstructed by the SpecFormer that has not been trained by UDL, and step 2 represents the HSI reconstructed by the SpecFormer that has been trained by UDL. The visualization results demonstrate the UDL's ability to enhance the reconstruction quality in texture-rich and edge regions.